Hello, Tanya Laird here, and welcome to Part 3 of Lecture 7 of ENGR 231 Engineering Statics. In this part of the lecture, I want to look at a few special conditions for forces when applied to rigid bodies. And these are the TwoForce Body and the ThreeForce Body. So first, I want to look at the special case of a TwoForce Body. And this will be especially important when we start looking at trusses in a few lectures. So let us consider a two-force body here. So let's take a look at a generic rigid body. And to this, let's say it has a center of mass at some arbitrary location. And I'm going to go ahead and apply two forces to it. Just two forces at some arbitrary angles and at some arbitrary location. So we have some F. And I'll say there's a point A here. We have an FA applied at A, and some point B, we have some FB. Again, just arbitrary forces. Now, if you remember from earlier in the course, we've mentioned that if something's to be in equilibrium, it must be in equilibrium about any coordinate system. So if something is to be in equilibrium, an object must be in equilibrium about any arbitrary axes. Be in equilibrium about any set of axes, any set of parallel axes. And this makes sense if you think about it, because when we define a set of axes on a object, or imagine the object. So in the room you're in, look at an object to your left, to your right, in front of you, behind you, whatever you're looking at. Maybe even look at the computer monitor or tablet or whatever you're watching this video on. Imagine drawing a set of coordinates on that. Well, and then crafting equations of equilibrium describing that object and how the forces in that object are distributed, etc. Well, nature doesn't care about how we define a set of coordinates. Nature doesn't care if we define the axes, horizontally like this, or nature doesn't care if we define the axes like this. Those are just mathematical models that we create to help us understand and analyze the forces that are present on a body. Nature doesn't care about that. Nature's just going to, the real universe, forces are just going to do what they're going to do. Nature doesn't care whether we've defined, X as to the left or X as to the right. Nature doesn't care. Nature's just going to do what nature's going to do, regardless of things like mathematical models or things like XY axes, XYZ axes. These are just our way as humans to understand the world, or some way to analyze a real object. And so the set of axes we choose ultimately doesn't matter. And so if something is to be in equilibrium, it needs to be in equilibrium about any set of axes if it's going to remain in equilibrium. There should not be some set of axes that we can draw that maybe an object is in equilibrium about one set of axes, but it's not in equilibrium about another set of axes. So what that means is, if I want to show an object is in equilibrium, I don't need to check every single set of coordinate axes. That's impossible. There are an infinite set of possible axes, because we can set an angle at whatever we want. So all I really have to do to prove an object is in equilibrium is prove that it is in equilibrium about any two perpendicular axes. Well, for 2D systems, any two set of perpendicular axes. For a 3D system, any three set of axes. So all I have to do is show that a body is in equilibrium about any set of axes. And if it is in equilibrium about any set of axes, that object will be in equilibrium. Now, the reason I mention that is that I'm going to choose a particular set of axes. And then the reason for this is that it makes the trigonometry a lot easier. I am going to choose a x-axis for this that passes right from A towards point B. So I'm going to use this as my x-axis. And this is just going to make the math a lot easier to handle. And so we can just, otherwise I have to use two sets of angles, and it's not impossible, it's not undoable, but it's just more headache than we need. And I'm trying to keep this video to a reasonable-ish, well, for my videos, reasonable-ish length. So let's go and redraw this with our now local set of axes. And I'm going to ignore the body and look at only the force, or the two forces. And I'm going to say that these are separated by some distance L. So we have two forces at just arbitrary angles, but off at some distance L. And I'm going to do this derivation for a 2D system, but the same thing would work in 3 dimensions, but the math would be a bit more complex, and we have to use cross products and things like that. And you can work through that if you wish, but I think I like to work through this just on the 2D to illustrate the basic concept. 3D works just as well, but you have to use a little bit more complex math. Okay. So let's say we have our two forces, and you know what, I'm going to go ahead and maybe show an axis here, or show a negative set on these as well. So we have our positive x-axis here and our positive y-axis here. We have point A here, we have point B here. And then these things are separated by some distance L between A and B. And we have some forces, and I'm just going to show these at arbitrary directions. And let's say I have FA here and FB here. And again, the directions are totally arbitrary. In fact, I'll try to draw it similar. You know what? I'll try to draw it to a similar direction to what I had here. So this one was almost horizontal. So FA here. And I'm going to say this is some theta A above the axis. And then I have B. If I can manage to draw a straight line. FB here. And some angle theta B. So FB and theta B. FB and theta B. Now, so we have this, and that's all well and good, but I want to start by doing a balance of moments. Now, if you remember from previous discussions, these will have both an x and y component. So actually, you know what, I'm going to go ahead and draw those components, maybe draw those a little bit separately. A little different color, maybe I'll draw those in green. So I'm going to separate out the x and y components here. So I'll have an x component or y component here that will be FB times the sine of theta B times sine theta B, and an x component that is FB times the cosine of theta B times the cosine theta B. Then here I'll have something similar, an x or a y and an x component. The y component will be FA times the sine of theta A, and the x component will be FA times the cosine of theta A times cosine theta A. Now, what I want to do is I want to apply a balance of forces and a balance of moments to this, and I'm going to start by doing a balance of moments. So let's do a summation of moments about point A and see what kind of moments are applied to this. And if this thing is going to be in equilibrium, as we saw in the first video of this lecture, if something is going to be in equilibrium, it must be in equilibrium about both translational and rotation. So it must be in equilibrium for both forces and for moments. So the moments produced by all the forces at any point must sum to 0. And I'm going to look at point A right now, and let's consider the moments about point A. Well, and when you're doing this kind of component method, you need to look at both the x and y components of this. And so let's look at this. Let's look at the moment generated by the x and y components. The x component of this, of both forces, their lines of action pass through point A, so they will not generate a moment at point A. We know that when a force's line of action passes through a point, it will generate no moment there. Same thing with the y component of force A here. So the y component of Fa generates no moment about point A. So the only force that has any component left, or the only force that will produce any moment, is the y component of Fb. So basically I have Fb sine of theta b and nothing else. This must then equal 0. Fb sine theta b is equal to 0. Interesting. So the y component of this force must be equal to 0. Now, I basically have two ways of making this equation true. I could either I have two things, the force or its theta. So I could make the force equal to 0, and then the theta can be whatever it wants, but I think I would call that a trivial solution, where obviously if I make the force equal to 0, if I make all the forces equal to 0, the thing will be in equilibrium, but I think that's a bit boring, so I'm going to reject the trivial solution, Fb being equal to 0, but there is another way to make this true, and that's to cancel out the Fb and say that sine theta b is equal to 0, and if you remember our trigonometry, that would mean that theta b is equal to 0, either 0 degrees or 0 radians, because of course sine, if you remember our trigonometry and our unit circle, sine of course goes like this, starts at 0, 0, etc., etc. And so the only way for this to be true, again, the only non-trivial way for this to be true, is if the if we're ignoring the option of the force being equal to 0, is if the theta b is equal to 0. Interesting. So now we know that theta b is equal to 0, that the theta for the force b is equal to 0, which means this force b is actually right along the axis. Interesting. Again, the axis that is local to this, that it points between or along or from point A to point B. Let's do the same for point B, or for the moment about point B. So the summation of moments about point B, if I can quit from jumping ahead, the summation of moments about point B. Let's see. So the y component of the b force will not generate a moment because its line of action goes through point B. Same thing with the x component of force B and the x component of force A. Neither of these three forces will generate any moment about that point. Next, so the only thing that will be there is, actually, if I was to be technical, I probably should have put a negative on there, because this was about point A, that was a clockwise and a negative moment, although that just cancels out with the FB there. So doing a summation of moments about point B, all I have is FA sine theta A. Oh, and oops, excuse me, there is also an L. Sorry about that. No, I cannot moment today, apparently. We need both a force and a distance. Sorry about that. I apparently can't moment today. And I'd also reject the trivial solution of the moment arm being equal to 0. So let's get this moment for right the first time. So summation of moments about point B. Sorry, I was kind of thinking ahead there. If I do the summation of moments about point B, the only thing that will have a component or a non-zero moment is the y component of force A. And that's going to be Fa times sine theta A times the moment arm length L. And this must equal 0. And if again, if we're rejecting trivial solutions of either the moment arm being equal to 0 or the force being equal to 0, we're left with sine theta A being equal to 0. Sine theta A must equal 0. And if we go and solve that trigonometry, of course we know that theta A must equal 0 degrees. So right now, we know that both FA and FB are right along the axis. Now, we haven't considered yet the direction of these things, whether they're going, we haven't considered direction, but we've just looked at, initially I assumed a direction like this, but if I initially set up FB going the other way, I would have almost a negative, and then, well, even that would cancel out. So let's just go ahead and do a summation of forces in the x direction then. So in the x direction, I would have Fa cosine theta A plus Fb times the cosine of theta b. But I know both these thetas are equal to 0. Oh, and that must equal 0. I know both these thetas are equal to 0, which means both of these cosines are equal to 1. So basically, I have Fa plus Fb is equal to 0, or Fa equals negative Fb. So this is what I really wanted to get to. FA equals negative FB. Or in other words, these must be equal and opposite. So this is a very rudimentary and, as we can see, crudely rendered proof of the two-force body condition. But the basic idea does hold true. For the two-force body condition, can be stated as follows. If two and only two forces, so not three, not one, not five, but two and only two forces, and also no couples. If you throw a couple in there, it screws it up. And only two forces are applied to a body those forces must share a line of action and be equal and opposite for the object to be in equilibrium. So if I'm going to have a generic rigid body with a center of mass here, if I have two forces applied to this, and again, two and only two forces, if I have a force and a force, the only way, if I have two forces, that they can be in equilibrium is they share the exact same line of action and they're equal in magnitude and opposite in direction. Anything else, and this thing will not be in equilibrium. So let me give you a simple example. So let us say I have a maybe you've seen one of these before, like an example of somebody setting up a diorama or some carefully balanced apparatus or something like that. Like, imagine I want to hang a flat plate, like a thin piece of cardboard or a thin aluminum sheet or any kind of thin object, just a thin planar object, like a thin steel sheet, something like that. Imagine like a piece of cardboard, a cookie tray, a foam board, anything like that. So you have an object that is very thin, and I want to do something cool. Like, let's say hanging a rectangle would be easy enough. If I want to hang a rectangle, the only way to hang that thing so that it's balanced, let's say I want to hang it so that this thing, looking from above, if here's the ceiling, or looking at it from the side, let's say I want to hang this object so that I could hang it from a single thread. And I want this thing to stay horizontal. So let's say I want to do that. I want to hang this thing, I want to hang a thin plate from a single thread from a ceiling and make sure this thing stays horizontal. The only way I can do this is if I hang it such that its center of mass is directly below the chord. So if that's a rectangle, if it's a rectangle, that means I have to hang the chord in the center of the rectangle, because the center of a rectangle, or the centroid, or the center of mass of a rectangle, is right at its center. No big surprise there. And we can do the same thing for triangles. There are equations for calculating the centroid of a triangle. And so you'd want to hang the triangle from its center of mass as well, from where the bisects equal, and etc. And depending on the complexity of the shape, it would have to be, you could get really interesting forms and things like that. But the reason for that, maybe let me draw this a little bit larger, so we can actually see this. So I can have some room to draw the shapes here, or to draw the forces. Again, this is if I want it to hang horizontally. So let's say you have your object with its center of mass here. Well, the thing about the center of mass is this is the center, well, it's right in the name, it's the center of mass. And so gravity always acts downward through an object's center of mass. Again, gravity always acts downward through an object's center of mass, and so it acts as a vector pointing through the center of mass downward. And so if I go and try to, look what happens though, if I try to apply a tension at some location, say to the left of the center of mass. If I do that, well, this no longer, I have a two-force body, but it's not satisfying the two-force body condition. I have two forces, and they may be equal and opposite. The tension would actually have to be equal to the mg, the weight, but because it's not directly above it, this thing's not going to be in equilibrium. What's going to happen is I actually have a couple now, two forces in equal and opposite, but separated by a certain distance. This thing is going to rotate, and it's going to rotate clockwise, and this thing is going to end up, off at an angle like this. And the same thing if I apply the tension, if I try to hang it this way with a cord like this, well, now this thing is going to want to rotate counterclockwise, and this thing's going to end up, at that angle there. And if I'm trying to make this thing hang nice and horizontally, that's not going to work. If I want to hang a thin horizontal object or a thin plate horizontally via a single cord, the only way I can do that while keeping that in equilibrium is to hang it right above the center, or right above the center of mass, or right above the centroid, equivalent terms in this context. So again, that's the basic idea of a two-force body. If you want to have only two forces on a body, you need to make sure that it's that the center of mass lines up with the supporting force. And that's the basic idea. And in fact, that's actually how human beings stand up as well. Even when you're, it's actually kind of an interesting thing to think about. If you you can actually see this if you want to pause the video after this and play with this. You might, if you are easily amused, this might amuse you. Oh man, I'm gonna try to draw I'm gonna draw a person. This is gonna be horribly wrong, but a person is only able to stand up if their center of mass is above their feet. So if you're just standing here, and if you're a crudely rendered person like this, and you're just standing there, your center of mass is going to be above your feet. And so, now, what if you want to lean forward? What if you go and lean forward? Let's go back. The center of mass is above the feet. And the reason for this is that your feet are the source of your normal force. There is a normal force, but that is holding you up against the floor. And your weight is acting through your centroid, which is which is in almost all cases in your torso somewhere, maybe probably near your gut or something like that. And so that's where your weight is acting through. Now, what happens if you want to lean over? Well, if you ever actually look at a person leaning over, the way it works is, even as they lean over, their center of mass still remains above the feet. And so they kind of, oh man, I really can't draw people at all. Oh my god, this is awful. Wow. So let's see. How does a person lean over? Let me think about this. Okay, so yeah, kind of like yeah. Okay, that'll work, sort of. I'm trying to think about how I lean over and I'm bending over and trying to imagine how this works. Okay, yeah, that works. Okay, so how this kind of works. Wow, I am really bad at human anatomy. Okay. There is a reason I'm in engineering and not medicine. Okay, so you kind of bend over like this in your weird alien human torso thing here. And you bend at the knees while you lean over. You do this kind of thing here. Wow, that is a horrible drawing of a human body. Okay, well, I'm not winning any art awards. You do this kind of thing. You bend at the knees. And what happens is, well, again, this is not properly lined up, but what happens is as you bend forward, you kind of stick your butt out like that, and your centroid still ends up above your feet. And so your centroid is kept above your feet at all times. Now, it doesn't have to be directly above the center of your feet. Your feet are capable of exerting a variety of different forces. Like, if you think of the force distribution in your foot, it can do an even force distribution where there's like a constant force all the way along, a constant normal force all the way along your foot. Or it can do something where most of the force is on the back end or most of the force is on the front end. You can have a shifted distribution, and that does allow a great deal of flexibility in how human beings can stand, and any animal, I assume. And so you can have a non-uniform distribution, like if you were standing on, leaning on the balls of your feet, or not on the balls of your feet, on your heel, I suppose in this context. If you were standing on putting most of your weight on your heel, you'd have a force distribution like this. If you're standing on your toes, you would have an opposite force distribution, where most of the force was on the front of your feet. So you are capable, and that can help with, and your body kind of automatically does this, or you kind of automatically do this. And this is just a skill you have learned to do unconsciously as you learn how to walk. But basically, the way human beings stand up is that as you lean over, you just distribute mass to as you move mass forward, you also move mass back to keep your center of mass above your feet. Because again, if your center of mass is you are basically a two-force body. You have your normal force. That's the only thing you can exert force against the ground with, your feet. And then, unless you're crawling on your hands or something, if you're trying to stand up, you're basically a two-force body. You have your force on your feet, and you have your weight. And so in order to remain standing, the vector of your weight that passes through your centroid must be above your feet. But anyway, let's not have me teach human anatomy. I'll stick with steel design. And that is the basic idea of a two-force body. Next, let us consider the three-force body. Now, I could work through the full derivation of this, but I think to work it through it, you can if you wish, and the math would be very similar to the two-force body derivation. So if you've seen how to work through the two-force body derivation, I think you could work through the three-force body as well. So I'll just describe it here. And I won't work through a full proof, but I will illustrate why it occurs. The three-force body condition. And this one is less useful, say, for trusses, but it does have its applications. And the three-force body condition states that if three and only three forces are applied to a body, and only three forces are applied to an object, I'll go ahead and say to a body, those three forces must have intersecting lines of action. It's not as restrictive as the two-force body condition, but it does put some limitations on how the forces are distributed. Lines of action. So let me draw a nice large rigid body here. Actually, maybe even a little bigger. Like so. And let's say we have a centroid at some just arbitrary location. Not going to terribly matter for this problem. I'm not dealing with weight here. And let's say I have three forces, F1, F2, and I want to show their lines of action. And this one's line of action. So what would happen, so I have two forces here, and now these are not in equilibrium as they are, but because if there were only two forces, they would have to be pointing at each other and equal and opposite for this to be in equilibrium. But if I had a third force, I could bring this into equilibrium. Now, what would happen if I added a third force, but I didn't pass its line of action through such that it intersects the intersection of the other two? So imagine I had this force here in F3. Well, again, if something is to be in equilibrium, it must be in equilibrium about all points. So let's say I have this point, let's say I call this point O. If I do a summation of moments about point O, what's going to happen? Well, if I do a summation of moments about point O, F1 will not generate any moment about there, and F2 will not generate any moment about there, but F3 will. Look at that. There's going to be a moment arm. There will be a moment arm, and again, there will be a moment arm there. And for F3, it's not going to have a non-zero moment arm, but there's going to be nothing to resist that moment. So in order, equilibrium is fundamentally based on balance. If something is to be in equilibrium, there must always be one force, another force to resist any force. Forces cannot be unopposed. If something is going to be in equilibrium, you have to have balance. And so there should be no point where you can sum moments where there are unbalanced or unopposed forces. And if I try to sum forces, or not some forces, but some moments about point O here, F3 is generating a moment, and these two cannot generate a moment, and so this thing is just going to start spinning. Same thing if I look at where this force, so same thing, let me go ahead and show its line of action, I think. Let's go ahead and show its line of action, it'll even show it intersecting with the F2 line of action. If I sum moments about this point here, where the line of action of F2 and F3 meet, neither F2 nor F3 will generate a moment there, but F1 will, and this time F1 is going to send the object spinning in rotation. And if I sum moments about the point where F1 and F3 meet, F1 and F3 will not be able to generate any moment there, but F2 will, and F2 will send the object spinning into rotation. And so even if the forces, even if their magnitudes and directions are such that they balance and prevent any translational force, I will still have rotation. I'll still have rotational tendency, and thus this thing cannot be in equilibrium. So, as shown, this object is incapable of being in equilibrium. This cannot be in equilibrium. We cannot have three forces that don't have a common intersecting, don't have intersecting lines of action. So, again, in order to be in equilibrium, we would need something like this. We would need to have, let me go ahead and show this, F1, F2, F3. I'll try to show similar directions. F1, F2, its line of action here, its line of action here, and then an F3. Actually, let me just sort of trace it. Let me just kind of cheese it and trace the line of action and then draw the force. An F3 here. Now, there is no point where I can sum moments that will have an unbalanced force, because the only possible, so if I sum moments about any place outside of this point here, outside of the intersection point O, any point outside there, all three forces are going to generate moments, which means none of them are going to be, there's going to be plenty of moments to resist. There's plenty of possibilities for forces to resist each other's moments. And if I try to sum moments at point O, well then all three forces are going to have 0 moment arms, and so there will be no moment period on that location, and so it's going to be in equilibrium. So again, if I'm going to have three forces and only three forces on an object, the only way that can be in equilibrium is if all three forces they don't have to have common lines of action, but they just have to have lines of action that all intersect at a single point. And that is the basic idea behind the two-force body and the three-force body condition. And hopefully that will serve as a bit of background in the theory there. And these do have applications in many of the topics we'll look at going forward, especially when we get at trusses and basic frames. Anyway, I think that'll do it for this portion of the lecture. I just wanted to introduce and describe and go through a little bit of rough proof of both the two-force body and three-force body condition. And the fourth portion of the lecture, we're going to look at some examples of applying rigid body equilibrium to basic objects. All right, that'll do it for now. Let me know if you have any questions. I'll see y'all shortly for part 4. And as always, thank you.